So now we will start our second part. We'll start our second part of the lecture, and this part is a bit tasty because we will talk about plate bending problems. Problems. The difference between 2D elasticity and the plate bending is in 2D elasticity. When we have 2D elasticity, we have our problem like that, and the load is in plane loading. We have in plane loading. So this is the plane of the problem. So we have in plane loading. In plane loading, this results only at any point into two displacement, U1 and U2. Okay? And actually, we result also in two stresses, mainly sigma 11, sigma 22, and the shear stresses here, which is sigma 12, and our stress tensor is sigma ij. So actually we have u alpha at any point x, then we have epsilon alpha beta, the strain, then we have the stresses sigma alpha beta, and we have the traction T alpha equals sigma alpha beta times n beta at this point. Okay? In plate bending, we have actually our problem is like that, and the load is out of plane. This is plates in bending. It's much better to say it plates in bending, because sometimes they call here is plates only. They give it a plate, but in plane plate. So here, actually, we will start to have one vertical deflection. So we have here, this is, for example, x1 and x2. And now we have here, this is x1, and this is x2, and this is x3. So actually up to this is x3. Okay? Still, we have two-dimensional problem. It is not three-dimensional problem, because our involved Laplacian is two-dimensional Laplacian. So here we have U3, which is deflection. This is deflection. We still have two rotations. Rotation in this direction and rotation in this direction. This rotation, we give it U1, and this rotation is given to U2. And these are the positive directions in the theory of elasticity. Okay, this is very important. U1 in the direction of x2, and U2 in the negative direction of x1. These are the direction came from the theory of elasticity. Why is that? If you go to civil engineering, for example, this problem is very, very important in civil engineering, because all roofs we have are plates. So to be able to resist stresses comes to prevent this rotation. The double arrow here means rotation. The double arrow means rotation. That means this double arrow, I'm going to use the right hand rule. I'm going to use the right hand rule. This rotation, it means rotation like this. Okay? So in order to be able to resist this rotation, we place reinforcement bars, steel bars, in this direction. So to prevent rotation like this, so we prevent steel bars perpendicular to it to prevent it in this direction. So we prevent the steel bars in x1 direction. Because of that, we call it U1. Okay? This is very important. So we have two types of rotation, displacements, of generalized displacements. Deflection, which is displacement, vertical deflection, and we have two rotations, one in x1 direction and the other one in x2 direction. So here is not like elasticity. In elasticity, we have two displacements, x1 and x2, and both of them are similar. Here, we have U3 is different from U1 and U2. Okay, this is very important. But a side note, we could have something we call it coupled stress theory or micropolar theory of elasticity. In this theory, still we have our load is in-plane load, but here we have two displacement, U2, and we have rotation, U3. Okay, and now the rotation now is independent of U1 and U2. So we do expect the mathematics we receive in micropolar theory of coupled stress theory is very similar to plates. Okay, and take it from me. Once rotation appears with deflection, you will end up in mathematics to the modified Helmholtz operator or Bessel function. You will see it in the fundamental solution. Okay, great. So this is the type of displacements. These are the types of displacements we have. Let me just follow something here to have the same notation. That means we have two types of stresses. The first stress type is we have two moments. If you look at this, we have moment in this direction. This is, we call it M11, and this moment is M11 also. Okay? And what is the relation between moments and the stresses? The integration through the thickness of the stresses give us the stress resultant or the moment. So the bending moment is a stress resultant. We integrate the stresses through the thickness of the plate, so we take moment. Again, we have here another moment. This is M22. Okay, so this is M11 and this is M22. And of course, we have torsional moment. We have torsional moment. We call it M12. And we have torsional moment like this here. This is M12. If you look at, this is 3 dimension, for example. This is element for the plate. This is element inside the plate, a small element inside the plate. So in this direction, we will have bending moment. I will use the right hand rule. So we'll have bending moment in this direction. This is M11. Also, I'm going to use the right hand rule like this. So here we have this one, want to break this part, M22. Okay, the same element here. So we have M12 here, this one in plane in this area, like this. So it is like this. This is M12, is a twisting moment. This one is M12, is twisting moment. It wants to twist this here M11 and M22. They want to break this element. They want to break it. But this one, M12, it wants to twist this area. And actually, in civil engineering, we have to add these two terms, F11 and M12, together in order to place a suitable reinforcement to resist this kind of stresses. The same, we have to add this M22 to M12 in order to place suitable reinforcement for this plate, and this is, we call it wood armor equation actually. Still, this is not the only type of stresses we have. We have another type of stresses, which is the shear. We have two ways of shear. We have shear here, goes in this direction. We call it Q2. I prefer, instead of using Q2, I say Q32 as much because it is in the third direction. and we have shear here like this, and we have shear here is Q31. So we have two types of shear in the three-dimensional element here. I'm going to draw it. So this is shear in this direction, and this is shear in this direction. This is Q32 and this is Q31. So we have two bending moments, M11 and M12. We have one twisting moment, and we have two shear Q31 and Q32. Okay? Coupling the plate together with the two-dimensional, coupling these two together, plate bending and 2D elasticity, if we couple them together, we'll get shells. We'll get shells. Okay? We will get shells. If the bending moment is going to affect the normal force, in this direction is the normal force, we will have shells. We will have shells. We could have shallow shells, we could have spherical shells, we could have cylindrical shells, but life will be very, very complicated. And actually, to be honest, it's much better to use to solve it analytically, because traditionally we have very common types of shells. It's not very strange shapes of shells. But plate bending problem is very, very important in civil engineering, especially civil engineering or mechanical engineering. Okay,